3 layers and up to 30, or people have been trying like 500 layers. But typically it's under 30 layers, and typically this kind of nets are trained on a very huge data set, and these nets are becoming very popular recently because it is achieving state-of-the-art in many artificial intelligence and machine learning tasks, including like in computer vision, like in image classification, object detection, and segmentation, and like in speech recognition. Almost all the industry have deployed deep learning models into speech recognition servers, and then you also have natural language processing and stuff like that. So this is a typical deep net. This is called the Google net. It is the model that won the 2014 ImageNet classification challenge, and it has like 27 layers and around 7 million parameters. This is trained on like a million images to do a classification of 1,000 categories. This is a very difficult problem, and people do this kind of challenge every year, basically. This is a trend, like the challenge started in 2010, and since they collected this huge ImageNet data set, which contained more than 30 images and very fine-grained category labels. And originally, the performance is around like 25 or something here in 2010 and 2011. And then starting in 2012, people started to try deep learning models. And then the performance dropped almost like 10%. And increased almost 10%. So this is a big improvement. And starting at 2012, everybody's using deep learning. And those are all like you can see the performance is continuously increasing until like this year. People are claiming to surpass the human performance. This is the human performance. They can do this kind of claim because there's a crazy guy who trained himself to by looking at images in the data set and try to do the classification on the test set. You might think it's an easy task, but it's actually not easy because there are 1,000 categories. Imagine you have to give you an image, you have to choose one category out of 1,000, and those categories are very fine details. So it's actually very difficult. But actually, humans and computers are making different kind of errors. So it's not really that comparable.
Can you explain what the vertical scale is?
So this is the top 5 classification accuracy error. So basically, your model proposed 5 categories, and if any one of those categories is within the ground truth, then you get a correct. Otherwise, it's incorrect. So, like, so this is computer vision, and also in speech recognition, you have this kind of they call revolution because almost like here, almost for 10 years or something, people are making almost no progress at all because they reach a point that you're trying to squeeze something out of the models, and the models become so complicated until like this is around 2010 or 2009. People try deep nets, and then there's a huge improvement. And now people are in speech recognition literature. They are all using deep nets, and they're using very huge nets in convolutional neural network. If you unfold it, it's a very deep network in time, and people are training this kind of deep nets with including data augmentation. They're training those nets with like 20,000 hours of data. That means like if you listen 5 hours speech per cell, 7 days a week, it takes you like 50 years or something to consume all those data, and they're supervised data with labels. So it's kind of work, but this works. And if you do like a Google Now or Apple Siri, and they are all backed with deep learning models. So that's why people are getting very excited with deep learning, because as long as you have data, you have powerful machines, typically GPUs, you can do this kind of exciting stuff. And so that's why we're here talking about deep learning and doing deep learning in Chiyuan and Mocha. So So what's exactly a deep nest? So it's actually not very different from the old neural network. It's just layers of like sigmoids and linear transform and layer-wise nonlinearities. And what is different is that now people are using very deep nets with many layers, and they try different architectures, including convolution. Like this one is the model we used in 2012. This is the model we used here. It's like a convolution. You can have different pipelines, and you can have fully connected layers, and you can try all the architectures. And basically, what makes it possible is that I think in deep learning you can abstract this computation into layers, we call it, and then the computation you can implement the computation in this layer without caring what this layer is connected to. So you have those basic components, and then you can just specifying an architecture of the nets and connecting those layers, and you can do whatever. Like for example, the old Turing machines and logistical regressions and stuff like that are all special cases of this kind of architecture. You can do all the old models in this way by using only one layer here, but you can do much more. So fortunately, nowadays we have a lot of libraries or toolkit for deep learning, which basically they provide implementations for common computational layers, and that's the core. And then they provide easy way, like typically by either description of the architecture, or you can do it like in Julia. You can do it with Julia code to specify the network architecture, and then they provide high performance computation backend wrapper on top of GPU or distributed clusters, things like that. And so with those toolkits, you can do deep learning like even on your laptop, or if you have connection to a server, it will be better. And there are many very good libraries including so Caffe is a very widely used library that is written in C++. This is widely used in academia because it is open source and has very nice modular design. People typically adapt this to modify their own architecture and algorithms. And you have CXXNet, and in Python have a very popular library called Cyano, which does automatic differentiation for you. So this is typically a pain because in deep learning, the way you train a deep net is you use stochastic gradient descent, and you have to compute the gradient, which is computed by backpropagation. But for each layer, you have to compute the gradient of output with respect to the input, which sometimes can be painful and you can make mistakes. So these tools help you do this automatically, and there are many wrappers on top of this, and that has parallel interfaces you can play with. And then there's a library called Chiyuan, which is concentrated on doing high-performance computation. And there is a Torque 7, which is backed by Facebook, but it's it is a very fast convolution implementation by Fourier transform. And then you have a library from MATLAB, and then finally we have this library Mocha.jl. It's for Julia. So basically, there are many different libraries you can choose. A natural question to ask is, why do you want to use Mocha.jl? Of course, because everybody is here today, that's the primary reason you might choose a library for Julia. And actually, because this is written in Julia and for Julia, you can easily interpolate or interoperate with other parts of Julia and other packages. You have easy data manipulation process, like if you want to do some processing, pre-processing of a data by like subtracting the mean or whatever, and you can do that easily in Julia, and you can have a pipeline with Mocha, and you can do like interactive prototyping in iJulia notebook, And I'll show you a demo in a while. I think this is a very good, big benefit here is that this has almost zero dependency if you only want to use the Julia-based backend. You just type package add and Mocha and you're done. You don't need, like, if you ever try to install Cafe, I tried that once, and it has a large amount of dependencies. I even need to recompile a customized version of GCC because the GCC on our server is not compatible with the requirement. I don't have administration right to reinstall another version of GCC, so I need to recompile the local and stuff like that. But for this, you don't need to do those stuff. And as long as you have Julia installed, you're okay. And then it has multiple backend. If you want to go for performance, you can switch to CUDA backend. And the most computational bottleneck convolution operation is backed by the BNN library, which is provided by NVIDIA to provide very high performance convolution computation. Actually, the convolution in Cafe is also using this library. So, in terms of performance, it should be matching here. And of course, you care about correctness. We don't have. I think there is a Julia summer project this year in doing automatic differentiation, but we don't have that in Julia now. So we do the gradient computation in Mocha manually, but we have this unit test to check the correctness. So you will not need to worry about the correctness, and then we have modular design, and actually the architecture is inspired by Cafe. So you have layers and activation functions, and you can specify network topology, stuff like that, and you can define your own layers or your own loss functions or your own solvers like that, and very easily. So, so Mocha, just type EKG add Mocha, and then you should be fine. And if you want to try the latest development version, you use EKG checkout. You will check out the latest code on GitHub, and then you can run EKG test Mocha. And it does a lot of unit tests. It takes a while too long, but if everything works fine on your computer, then you should be fine to go. And now I'm going to show you iJulia example. So basically, this is an example of showing how to use a pre-trained model. So this is a pre-trained model trained on the ImageNet classification task. So basically, because this is a very big model, and it does like 1 million images, and it takes like a week to train, even on a high-performance GPU. So I'm not going to show you how to train it. But this is a pre-trained model, and we just do a load. Okay. So we will load the model, and I'll show you how to load the model and try to do classification with the trained model. So basically, you start here by specifying by using Mocha, and you initialize a backend. Here we will use CPU backend because it is the easiest one to use here, and we initialize the backend. Now you can see there will be some output. It is not enabling the CUDA backend. It is using the CPU backend and stuff like that. And then we will define the layers, the network here. So you can see it is a very huge network. I don't remember how many layers here, but it starts with, so basically all the network typically start with a data layer, which provide the data, and some computation layers. So here we crop the image, and we do convolution and pooling and stuff, and convolution, a lot of convolution. And then fully connected layer, which are called inner product layer here. And then in the end, you have a softmax layer, which gives you a 1,000 way
normalize the probability, which so basically it is computing the probability of those 1,000 categories given an image here. And the way you construct a net is just by specifying a name and the backend and the layers here. So here I'll run this code. So here's some output. So this network has 16 layers, and I printed network here. So here are the basic summary of the network. This is useful for debugging, especially when you want to know the size of the network, output, input, size. And then you can actually visualize the network by like graph viz. And here we have, we can actually output this. There's a package graphviz.jl use a dot to visualize, but I'm not able to make it work, so I will write it to a file and load it here. Yeah, oops. The images library takes a while to load, I think. Yep, I run it again. So here you can see the visualization of the network. It starts with a data layer. So in each layer you have a bottom, which is the input, and the top, which is the output. So data layer doesn't have any input. It just provides the data, which is 2,506 by 2,506 color images with 3 channels. And this is the number of mini batch size here. And then it is cropped by, to 227. And then you have a convolution, pulling basically subsum the convolution, the output, so it from 55 goes to 27. And then this is the normalization layer, and another convolution, another pulling, blah, 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 convolution, a lot of convolution. And then in the end, you have softmax, which normalize the prediction numbers to a probability distribution. And this is boring. Now we define the architecture of the network. So the architecture of the network in Mocha is basically specified by defining layers here. But the order of the layers actually doesn't matter. What matters here is the how. So in each layer, you can see in each layer you have some output blobs an input blobs. You specify the name of the blobs here, like you specify the top blobs have a name called FC6, and the bottom blob called Pool5. And those names are actually define how you connect those layers. And you will have a cyclic directed graph here, and by specifying the connection here, and it will automatically sort the layers by topological sort in a correct order, and it will check the topology when you define the network. Now you have defined network, and we just load the pre-trained model here. This is actually a imported pre-trained model from Caffe. You can just load it by opening the HDF file and calling the node network function. And you can see, yep, it is loaded. And now we're good to start doing classification. And in order to, so the classification is a 1,000-way classification. It is just 1,000 numbers. And each number corresponds to a category here. We read the category from the text file, and you can see those are categories, 1,000 categories in the ImageNet. And then we use a very simple wrapper on top of the net to do classification, basically. And we read an image here. It's a cat, cute. And then we basically, now the image is the cat we just read. And now we just do classify with the classifier. You can see the classifier is constructed with this net, which is loaded from the pre-trained net. And then we print the class. Okay, the class is, yep, tabby cat. So it's correct, unsurprisingly. And now we can actually do some like more analysis. Like you can plot. So here I use Gadfly to do some plot. Basically, you can sort the output of the 1,000-way softmax and plot the top 5 probability output, and you can actually specify and see what are the top 5 proposal categories this network produce, and that gives you a sense of what is going on here. And Gadfly takes a while to load. Okay, load it. Yeah, so you can see that those are the top 5 probabilities predicted with these images. Those are the corresponding labels. You can see cats, tiger cats, and Linux, and cats, and they're all cats. So basically, this is this is also shows why this kind of problems are difficult for human. I mean, imagine, are you able to distinguish between all those different kinds of cats when presented with an image? But the deep nets are able to do some very fine-grained classification here. And this is another example. A bird, and then it classify as those kinds of birds, which I have no idea, but but they're birds. Yep, here you go, bird. Okay, so this is an example of showing you how you can do interactive manipulation on an iJulia notebook. It is very easy to use. You have instant feedback visualization, and you can plot the architecture of the network. You can change the architecture and do all kinds of experiments. That's all because it's powered with Julia, and you have a very nice interoperation with Julia. And now I'm going to show you an example of, it's a smaller example. It doesn't take a week to train. This is sometimes called the toy model when people do deep learning. This is MNIST handwritten digit classification. This is a very easy task, like a very dumb model, like 1 year's neighbor gives you like 90-something performance accuracy. But this is a very, it's not so small. It contains, I think, 60,000 training images and 10,000 test images, and you can train a network to basically to classify those 10 digits. This is a 10 classification problem, and I will show you walk you through this example here. And basically, each image is a 28 by 28 grayscale. It's one channel image. So images in Mocha is represented by a 4D tensor. Basically, it is width by height by channels and by batch. Batch means mini batch when you do stochastic gradient descent. So here, each tensor is 28 by 28 by 1 and by 64. And Mocha actually supports general n-dimensional tensor for arbitrary data, not limited to images. And Mocha uses HDF file to store the data, but actually you can use whatever data format you prefer, as long as you can write a data layer as the data provider here. So basically, when you convert, we have by the way, all the examples I show here have example code in the repo. You can have a look at it afterwards. And there's a script to convert the official MNIST dataset to HDF file format here. And after you have the HDF file format, you can define a HDF file data layer, which basically you specify the source, which is a TXT file containing a list of HDF files you want to read. This is this way because sometimes you have a list of a bunch of HDF files and you want to use as a training data. And this is asynchronized data layer, which means it uses the asynchronization capability of Julia to, it's single thread, but it can read data while you are doing waiting for a computation on CPU or GPU, so it is very efficient. And we specify the batch size to be 64 here. So basically, in each iteration, 64 images are read from the disk and feed to the network. And then the network we use here is called LearnNet. It's a network proposed by Yana Kun in 2000. No, it was in 1998, very old one. And it's basically a convolution net. So a convolution net, I'm not sure, maybe everybody is familiar with that, but basically it is instead of a fully connected neural network, it has a local filter here, and the filter is run through all the images. And this is a 2D convolution operation. That's why it is called convolution nets. And then you have a subsampling net. Nowadays, people call it pooling. Basically, you take the max in each local region. This gives you some local shift invariance here. And then you have another convolution and the pooling, and then fully connected to give you the 10-dimensional output prediction. So basically, in Mocha, how you define a convolution layer is just by defining a convolution layer. And you can specify the number of filters here. Basically, that is the number of dimensions in the convolution output. And then the kernel size is the size of the filter. Here is 5 by 5 here. And then the bottoms and the tops are just the names of the input and output I just described. And this is specify how the network is connected. And then on top of the conv, which is the output of convolution layer, you have a pooling layer, which is the subsampling. And basically, you specify the subsampling local range. This is the width by height. And then the stride means the number of pixels you move after you do the subsampling. So basically, there's no overlap here. And then you specify the top and bottom again. And pooling, by default, use the max pooling. And of course, there are many different other ways of doing pooling. For example, you can do mean pooling. You can specify mean pooling by adding this parameter to the definition of the layer here. And then, so basically, this is a visualization of the network we're going to use in this MNIST handwritten digit recognition task. Basically, it starts with a data layer. So as you can see, this is very similar to the image classification example we just showed. And there's a slight difference here is that in the data layer, you are not only providing the data, you also provide the label, because in training stage, you have the label here. And the label directly connect to a loss layer here. So the loss layer compute the difference of the prediction of the label, and then back propagate the gradient through the layers and update the parameters of the network. And that's how it works. So basically, you can see it's a convolution pooling, another convolution, another pooling, and two inner product, which are fully connected layer, and then you have a softmax loss layer here. So the rest of the layers are defined as conv2, pool2, the same way, just different kernel size maybe, and different, actually not different, a different number of filters. And then the fully connected layers are just an inner product layer. It is a linear transform plus some activation element-wise nonlinearity here. In old days, people use sigmoid here, but nowadays people are more and more prefer this rectified linear unit. This is a very simple function. This is just a max of your output with 0. So if it is negative, we set it to 0. Otherwise, we keep it the same. And they found this is to be very effective in training, especially large-scale network. And we use this. So you can specify. So basically, for each layer here, you can specify a neuron. If you don't specify, it's an identity which doesn't change. You can use rectified linear unit or sigmoid or whatever you want, or tangent edge. And then another inner product layer. We don't specify a neuron in the prediction here, and then we use the softmax loss, which is basically it's like a logistic regression on the top layer here. And then after defining the network, you specify how the. I want to mention here is that there are many different ways of defining a network architecture. Some toolkits prefer to use a config file. I prefer to use this Julia language to define layer here because you can do it You can program, I mean, sometimes you can have a parameter of generating 5 layers, 6 layers, and you can just do that in Julia language. You have a for loop or whatever here, and you can be very, very flexible here. And now after defining the architecture of the network, you define how to train it. Basically, it's typically trained with a stochastic gradient descent, but you have some other variant here. But now we have 2 different solvers in Mocha, but you can actually define more if you want. Typically, SGD works fine, and it has many parameters, like max number of iterations to run, and the regularization coefficient. And you can have a momentum in your training. This is found to be very important nowadays. And you have the learning rate policy, which specifies the base learning rate and how it decays. There are many different policies. The policies I prefer is there's one policy that tests the performance on the validation set during training. If the performance on the validation set decays, then it makes the learning rate half. And that's a very useful learning rate policy, and I'm not showing that here, but you can find it in the document. And then there's a load from parameter, which specify, because during training, it sometimes takes a very, very long time to train, maybe not for this example. And so the Mocha will periodically save snapshots of the training model. So if the computer crashes, or if you have a power loss or whatever, or if you want to run more iterations, you can start with the previous saved snapshot. And this will automatically load the latest snapshot from this directory. And then you define a solver with these parameters. And then coffee break, but not for us. Coffee break for the solvers. This is like when the solver is busy computing your gradient updating parameters, so we give it some opportunity to stop and do something else. Basically, if you set up a coffee launch for the solver, all your training statistics parameters will be saved to this file, and you can come back and you plot like the curve of the learning, how it converges and stuff like that, and you can inspect that. And then you can add some coffee breaks. Like the typical ones are like you want the solver to show you the training summary, like what is the current objective function, what is the current learning rate and stuff like that, maybe every 100 iterations. And you want to show, maybe save the snapshot every 5,000 iterations, and maybe you want to do a evaluation on the validation set every 2,000 iterations, stuff like that. You can also customize your own coffee break, and you want to do some fancy stuff like that. And this is maybe it's not very visible. This is an example of I took from the document, and this is how there's a script you can use the saved statistics to plot the learning curve here. So basically, this is the number of iterations, and this curve shows you the objective functions, and this shows it converges very quickly, and then it basically takes a very long time in the end. Yeah, I can show you. So this is the code here. Basically, how you train the code, we will run with CPU first. Julia. So we'll load Julia and load set up layers, and those are the log output. And then this is the initial objective value before training. And this is the initial performance before training. It is 10%, it's basically chance because there are 10 categories. And then it starts training. Because I specified doing a training summary every 100 iterations. So you can see like this is the first 100 iterations, and this is the objective function value, and this is the second 100 iterations. It is it takes about like 6 seconds to run 100 iterations on the CPU. It's okay for this kind of scale of models here. Then we can actually run on GPU here. It is very easy. You just do this. Actually, what this parameter do is that when you instantiate a backend, you can just choose between GPU backend and CPU backend. Is that visible? Yep. And then we're done. Now I'm running this on my laptop. So this laptop has a NVIDIA graphic card, which has maybe not so great GPU here, but let's try to see. So the same thing here, and loading, and the same, almost the same performance, and you can see it's faster, almost 1 second per 100 iterations here. And if you have a servo access, like we have a servo here. This is a very good GPU. Maybe not the best. I don't know it's K20 or K40, and we can run probably on the servo node. I hope it works because they are doing maintenance today. So from the log, you can see the CUDA is loaded. And you can basically specify loading CUDA by defining an environment variable. And it takes a while to initialize the CUDA. Yep, good. Okay, setting up layers. Okay, starting. And then this is super fast. I think it runs roughly 300 or 400 iterations per second. You can see it's almost 98% accuracy after the, I mean, it's really fast if you have a GPU card, and it's like a 20 to 30 times faster than the CPU code. And of course, you can do multi-thread CPU, but that's what you can do with GPU. And this is the demo. And just some details, like you can do parameter sharing in Mocha, which is very important when you want to do like pre-training or fine-tuning existing models, and you want to have more advanced architecture like recurrent neural network. We haven't implemented that yet, but in theory, you can do that because we have this kind of primitives, and this is a visualization of how the parameters are showed. Basically, when you define a layer, you specify a name, and then all the parameters under this name is registered globally, registered in the backend. Then you can share that when you do another network with the layer of the same name. And finally, we are the third most popular packages, Julia packages, and and any contributions are very welcome. Thank you. Sorry?
Did you do performance comparison on fully devices versus storage or nearby systems?
Performance comparison with different devices, what?
Okay, so do you have benchmarks versus other implementations?
Oh yeah, I mean, so for CPU, I did some comparison with Caffe. It's roughly the same. For GPU, it's almost the same because we use the same cuDNN from NVIDIA to do the bottleneck computation. So I didn't do a very rigorous benchmark, but like looking at the logs, like how many 100 iterations you run, roughly MNIST and other models like CRF10, and it's roughly the same to Caffe, which is pretty fast. Not the most, the fastest you can have. So basically, we didn't implement that yet because nowadays, most of the time when you have people use GPU to do computation when you train not large net. The GPU cluster implementation is still an open problem because you need very high-speed hardware connection between GPUs to make it really work. Otherwise, you don't actually get linear scale. So we don't have that yet. Basically, we do on a single GPU, and we have it's on a single node.
Neat question. How do you know how to define your network layers?
So it's oops. Maybe it's why I'm doing a PhD.
So you said that one of those image classifiers was approaching human performance. You mean like the performance of one human?
No. Yeah, the question was what does it mean when the image classification approach human performance? It's not like they do a very rigorous comparison by asking a lot of human to perform the classification. It was just there was a crazy guy who did this torch by forcing himself to look at the training set for like a week or something, and then he tried to classify several thousand images, and he reported a number there, and then people are comparing to that number, and it's not a fair comparison anyway, but that's just to attract popular attraction.
Hey, any further questions? All right, thank you.
Thank you.